Thank you for inviting me, Vincenzo, and thank you all for attending. I'm going to present you today my recent paper called Small Task Incremental Learning that is currently on archive. So first of all, who are we? So we are a small team. Myself, I'm Arthur Douillard. I'm a first-year PhD student at Sorbonne University in Paris, France. I'm also a research scientist at Euretech. So Euretech is a company work on fashion, and the goal is to understand what kind of fashion people wear on Instagram. And we need to add a new kind of clothing, new shoes, a new dress every week. And therefore, we need continual learning in order to add it very quickly. My advisor is Mathieu Corde, who is a professor at Sorbonne University. And my other colleagues are Charles Lyon, Thomas Robert, and Eduardo Valle. So first of all, I will describe what is the task, what is our setting. As in continual learning, there is a various and very diverse kind of setting. Here, you can, there is two famous setting, which is either a new instance setting, where with each task, we add a new instance, so new sample, but from existing classes, or there is a new class setting, where each task brings new classes. This is the setting that we adopt. Meaning, like, as you can see on the image here, first of all, we train on a subset of tasks, so task from 1 to 50. Then on task 2, we train new classes from 51 to 60, and until we see all the class. So every time we add a new kind of classes. Contrary to some methods, we choose to reuse a limited subset of previous classes data. So we don't reuse the whole data from previous classes, as it will be kind of cheating and will defeat the purpose of continual learning. But we use a very small subset that is preserved into a memory for rehearsal learning. So as you can see here on the image, during task 2, we are training on the new classes, so from 51 to 60, but we are also reusing a few samples from the old class, from 1 to 50. And as you may have already guessed, the model is copied from task T to T+1. So between tasks, we are not reinitializing the model, but we keep the same weight that are fine-tuned through the training. For the evaluation, there's also several kinds of evaluation. What we choose is that the model is evaluated on all scene classes. So as you can see here on the image, for the first task, we evaluated on classes from 1 to 50, but on the task 2, we evaluate our model on 1 to 60, meaning that in task 2, we only see the new classes from 51 to 60, but we still must be good on all scene classes, so both current classes and past classes. Contrary to some methods, we don't have access to task ID inference, meaning that we don't know if a sample comes from the current task or a previous task. We don't know this fact, and meaning that we think it was a more realistic and more challenging setting where samples is unidentified and must be classified between all scene classes. And finally, we don't want to choose as a final score only the last accuracy. Because in continual learning, the goal is to be able to learn continually, like in lifelong learning. And it means that there is no real end of the training. Therefore, we don't want to be good only at some point, at some end, but we want to be good during the whole life of the model. Therefore, we use a metric called average incremental accuracy that was designed by iCarl in a CVPR from 2017. It's simply the average of all accuracies. So as you can see here on the formula, we're doing the average of the accuracy of the first task that is applied on 0 to 50 classes, then from the second class that is applied on between 0 to 60 classes, and etc. Finally, we are following the setting of Hu et al. So Hu et al. Is a paper from a CVPR from last year called Learning a Unified Classifier Incrementally via Rebalancing. In this setting, we are following the setting where we evaluate our model on 3 datasets, CIFAR 100, ImageNet 100, and ImageNet 1000. ImageNet 100 is simply a subset of 100 classes of the larger scale ImageNet. As said previously, we choose to reuse a limited sample from previous classes data for rehearsal learning into a memory. There are several kinds of ways to choose how much capacity for the memory we want to use. Obviously, the more capacity we have, the easier the continual learning is, but also it is less realistic. iCal defined a setting called mtotal, where for CFAR 100, the whole capacity for previous classes was 2,000 samples, meaning that the first task at first could use the whole capacity if they want, but the more tasks we add, the less images per class could be stored. We follow the setting from Hu et al., which is way more challenging, but maybe also less realistic, where each class, starting from the start, only have access to 20 examples from the previous data, no more. Because the amount is very low and the amount of new classes is very high, there is a strong imbalance between them, and we are almost in a setting kind of low shot for the previous data. Finally, for all our dataset, we train our model on half the total classes at first. So for CFAR 100, it will be 50, but for ImageNet 1000, it will be 500. And then once we have trained this one big task, and the model is quite parameterized, we can then incrementally add more tasks. But the goal here is to determine what is a realistic setting. And in my setting at Euretech, in my company, we usually add only a single choose per task. So every week I need to train on a new choose. But one choose, it's simply one new class. So that means that we have tasks that are very, very small, made of 1 or 2 classes, no more. But the less class we have per task, the more tasks we have to train. And the more tasks we have to train, it means that the life of our lifelong learning algorithm is way longer, and plus the setting is way more challenging. And this is a setting that we choose to focus, where we train with a lot of tasks made of a single class, which was, I think, never made before and very challenging. So first of all, we choose a baseline, and then we decide to improve on it. Our baseline was Hu et al. So as described previously, the CVPR from last year. Their model is called USIR, or actually, we name it USIR as they didn't give it any name, so we choose to give it this name. Hu et al. USIR is made of 3 components: a cosine classifier, which is simply some kind of a fully connected layer for classification. But here, the product is replaced by cosine similarity. This means that the features and the weight of the classifier are L2 normalized, and that means that projected onto a unit hypersphere, as you can see on the image. The idea behind this is that the magnitude of both the new class weights and the old class weights are normalized, and the magnitude are equal. Because they are equal, as you can see on the image, the bias toward the new classes is way less strong than it could be. Therefore, the accuracy between new and old class is better stabilized. Most lifelong learning solutions need also some kind of loss in order to constrain the drift of the model, to reduce the catastrophic forgetting. We don't want our new model to be too much different from the old model. Either, otherwise we will forget the previous knowledge. On the case, they choose to use the distillation, but it's applied on the final embedding. So the final embedding is the embedding that is after the global average pooling and is a flat embedding. And they are doing a cosine constraint, meaning that they are doing a cosine similarity, and the old embedding and the new embedding must be very similar to this metric. Finally, they add a regularization that is inch-based, where they want to reduce the ambiguities between new classes and old classes. This is the model that we choose to base on, and we choose to evaluate our model in the same setting with the same data sets. However, we choose to discard the inch-based regularization, as we found that it didn't bring much performance, and it was actually quite slow to train. So our model, we call it PODNet. So our model is made of 2 components, 2 major components. A classification loss that is obviously helpful to discriminate classes, and a distillation loss, 2 distillation loss to reduce the catastrophic forgetting. Here we call the classification loss LSC for local similarity classifier, and we call our pod distillation in 2 parts, LPod flat and pod spatial. Pod flat is applied on the final embedding and is actually equivalent up to constant factor to the loss that Hu et al. Used. So some kind of constant constraint. But our main innovation that brings the most improvement in performance is the pod spatial that is here applied on several intermediary embeddings of the ResNet, the ContinualAI. So first of all, I will focus on pod distillation, which I said is the main part of the paper and the main gain of accuracy. Previous loss from let's forget. So this is a loss that was designed by Hu et al. And is applied on the final embedding. So it's L2 distance between two embeddings. The embedding are L2 normalized. Therefore, the L2 distance is equivalent to a cosine similarity. This means that we want that the final embedding is similar pixel-wise to the whole model. But we found that this loss has several shortcomings. First of all, yes, the forgetting was alleviated by a large margin. But in order to make it work, it needed a very high loss factor. Because the loss factor was very high, the embedding was kind of frozen, meaning that the new model stayed very, very similar from the old model. But because it was too much frozen, the plasticity was hurt, meaning that the embedding didn't have enough slack in order to learn new classes. And this was a problem. Another problem that we found is that while applying a constraint only on the final embedding, if you look at loss that is applied on parameters, such as elastic weight consolidation, for example, they are doing some kind of constraint on the parameters of every layer. So why here working on activation, are we applying the distillation only on the last activation, the final embedding, and not on all embedding? So we want to design a loss that can exploit every intermediary embeddings. Furthermore, Hu et al. And ourselves, we know that we are working on images. Can we use this fact as a prior to improve our model? So this is my loss. First of all, if we want to generalize the let's forget loss to spatial feature, we can simply do what is called pod pixel. So here, our embedding is no more a simple vector of one dimension, but is a cube of 3 dimensions with a channel axis, a width axis, and a height axis. Here, we are simply flattening the cube, and we have a very large vector that is C times W times H, and we are doing the L2 distance between those two. But as you may have guessed, L-pod pixel is a naive generalization, and we can do better. First of all, no plasticity is left. So yes, we're working on a cube, so maybe there is more information than simply the final embedding after the global average pooling. But even with this more information, the plasticity is not very well used because here we're constraining that the old model and the new model have the same pixel. We want that exactly the same pixel are exact. But the problem is the distillation loss is considering that the old model is kind of an oracle, a ground truth. The new model should approximate what the old model was. But here, this is a problem because the old model is not perfect. Actually, it's far from perfect. The old model may be stuck in a local minima, maybe even a bad local minima, and we can do better. Therefore, we want to be less sensitive to pixel outliers. Like we don't want to approximate exactly what was the old model. Furthermore, I said previously that I wanted to use the fact that we are working on images as a prior. But here, yes, we're working on some kind of images with 3 dimensions, but we don't exploit the multiple dimension because it's simply flattening L2 distance. So then again, we can do better. Our solution was to do to avoid a pixel-wise match, but to doing distillation on some kind of statistics. The idea behind statistics is we don't want anymore to focus simply on this pixel should be equal to this pixel, but we want that globally the statistics stay similar. Because their statistics should stay similar, we are more robust to a different kind of pixel outliers. So to do this kind of statistics, our solution was to pull alongside the particular axis before distilling. So on images, we can see on the left the cube with a 3 dimension, and then we have different kind of pooling: channel pooling, gap pooling, which is global average pooling, width pooling, and height pooling. Those different pooling were tested, and we found that the best pooling, trading best the stability with the plasticity, was to pull alongside a spatial dimension. The first formula, L-pod width, we are first sampling alongside the width dimension, and then we are doing the L2 distance. This means that we don't want the two embedding from the old model and the new model. We don't want them to be equal pixel-wise, but we want that the statistics of each row of the image, of the feature, stays similar, meaning that a pixel can shift a bit to the right or to the left, as long as, in average, the statistics stay similar, we are okay with it. So it's more robust. Likewise, we can do L-pod width, but for the 8. So it's simply a matter of switching the two summation. Here, for L-pod 8, we are doing a summation alongside the 8 axis, and then we do the L2 distance. And finally, we found that the best solution was to use both of them. So we simply, for L-pod spatial, our final loss, we do the summation of L-pod width with L-pod 8. So as you can see here on the image, this is our two pooling results. And based on this, we are building our distillation loss. So first of all, we wanted to compare our loss to other loss that are based on intermediary outputs. So Huetal loss was applied on the final embedding, so it was not really comparable. We wanted to compare with pod pixel, which is the generalization of Huetal loss, but applied to the spatial feature, so the intermediary embedding with a 3-axis, channel, width, and height. We also compare with Daretal model. So Daretal model is in the paper Learning Without Memorizing. It's a CBPR from last year, where they are doing a distillation on GradCam. GradCam, for those who don't know, is a method for visualization where they're using the gradients and the activation to produce some kind of attention map. So it's a cube of several dimensions also. Those two techniques are very important and very interesting, and they work very well with large increments, but we found that it didn't work as well with a large amount of small increments. So in our setting, when we have a lot of tasks, but made of a single class or two classes, no more. Because in this kind of setting, the forgetting is very heavy. Recall that for CIFAR 100, if I want to add one class per one class, it means that the single class from the new class has 500 samples, while all previous classes has only 20 samples. So there is a very strong bias and imbalance toward the new class. So because the forgetting is very heavy, the only way to get a good global performance is to use a very high loss factor. But then the plasticity is often sacrificed to get just an okay performance. And we saw that our spatial statistics are more robust than pixel-wise distillation because they don't focus on some pixel outliers, but just on average. And they're also less rigid because we can reorganize the information of every pixel as long as, in average, the statistics stay similar. So we evaluated our model with two kinds of loss. So on the left, we are evaluating our different losses that are applied on the intermediary embeddings with pod flat, so with the cosine similarity on the final embedding. And on the table on the right, we're evaluating our model with only the loss applied to the intermediary embeddings, but we don't use here the final loss on the final embedding. As you can see, there's two columns for each table called LME and CNN. It's different kind of evaluation setting that I will describe later. But what is interesting and is common to those two evaluation settings is that we can find that losses that don't exploit statistics, but instead exploit pixel-wise match, such as L-pod pixel or GradCam, they barely improve the result of not using a loss, or they are improving by a very slight margin. And because we use a very high factor, yes, maybe we didn't forget too much of previous accuracy. This is very good because we don't have maybe a catastrophic forgetting. But if we cannot learn anything new, this is useless. And if we saw every other loss that is applied on statistics, all get a way better result by at least 5 points. So you can see that pod channel, pod gap, pod width, pod 8, and pod spatial all get better result. And what is even more interesting is that the loss pod width and pod 8 are very much better than the other, even without using a constraint on the final embedding, as you can see on the right table. And as you can see also, that using the combination of both the pod width and the pod 8 also improve the results. So we choose to keep the final loss pod spatial, meaning the combination of pod width and pod 8. Now that we have seen the distillation losses, we want to see what can we do more on the classification accuracy. So for the classification, we base our model on Hu et al. You see, where they have simply a cosine classifier followed by softmax and cross entropy. So this is quite classic, and it's a kind of a model that is very often seen in a few-shot learning or representation-based model. We found that there is a problem because even with the best distillation loss, the embedding distribution will change a little. And this is normal, and it's actually preferable, because if the embedding didn't change at all, we couldn't learn anything. But because the embedding distribution changed, the classifier must adapt to this changement. And we saw that from task 1, the embedding of each class was very close to the single majority mode. But then when we had more classes and more tasks, we saw that the embedding became stretched. Here, you can see that the color, the shape are the embedding of a class, and each marker, so some kind of star, are the centroid. So if you don't know, in a cosine classifier, because we are L2 normalizing both the weight and the feature, it means that the weight of the classifier are literally centroid that are in the same latent space as the feature, and that can be visualized here. This means that the cosine classifier is modelizing every class as a single majority mode. But because it works very well for the first task, but then for the new task, as much we add a new task and the distribution gets stretched, there is a lot of outliers that are very far from the unique majority mode, and this is where we have a problem. So, as said previously, the cosine classifier is too sensitive because of modeling a unique majority mode. So, our solution, our intuition behind this was to use a multimodality, meaning that instead of using a single mode per class, we will use several modes per class. So at first, if the class is very tight, all the modes can collapse into the same one. But if the class becomes stretched, as we saw in a lifelong learning setting with a lot of tasks, here the mode can be distributed uniformly across the whole distribution. And this is very useful because then we have a less forgetting because of outliers. How did we do it? So on the left, you can see that we did cosine similarity between the feature and a centroid of a class. And then on the right, what we do is we do the similarity between a feature and every mode of a class. Then all those similarity for the same class are aggregated together into a weighted average, which means that the mode that is the closest, for example, if we focus on the green class, the mode that is the closest to the feature will matter more, than the mode that is the further away. Because of this, we can grab every pixel outlier, every feature outliers that we have due to continual learning. So our hypothesis was that the multi-mode makes the classifier more robust to distribution change. And in practice, we saw that effectively we are more robust. Compared to single mode, we didn't find a single significant gain in new class accuracies. Therefore, it was not simply more capacity that helped us to learn more and more easily new classes, but actually we find a gain in old class accuracies, meaning that we forget less from previous classes. We thought that it must be simply because we add more capacity, because we add a little bit of capacity indeed. But if we were stacking several fully connected layers together, it did improve a bit the result, but it increased a lot the capacity, but we didn't find the same behavior. And here we are adding a bit of capacity, but it's capacity that is well used in order to make the classifier more robust to a distribution change. And we didn't do it, we could do it also, is some class may be less stretched than other, and we may choose to discard some mode and not use the same amount of mode per class. Note that we have here our model, so that was made in a similarity loss based on local similarity for each mode of a single class, and a distillation loss that was applied on intermediary embedding. We are now seeing the results. So I said previously that we evaluate our model as Wetal did with two methods. So the first one, NME, for nearest mean exemplar. It was a method that was introduced by ICARL in 2017, where they are doing a classification with a KNN on the embedding. Each ground truth for the KNN is based on the average of sample stored in the memory for rehearsal learning. Then we have the CNN setting, where here we're classifying with the classifier logits and with argmax. Actually, it's quite simple, but there is some trick to make it work, where we are freezing the weights of the all classes, and we are only, after each task, fine-tuning them without training the ContinualAI for a few epochs in order to make it work. So we evaluated those two settings, and we found that on small data sets, NME was way better. But as we go to larger data set, those with a larger model and with a larger embedding size, the NME with a KNN was less good than, was worse than the CNN. So for CPR 100, which is some kind of small scale data set, we evaluated both the NME and CNN. So CPR 100 has 100 classes. Therefore, we train at first 50 classes, then we choose to add classes incrementally. On the most right side column, you can see that like after the first step, we are doing 5 steps of each 10 new classes. Then on the left column, the most left column, we are doing 50 steps in addition of the first step with only one single class. So as said previously, the more tasks we have, the less amount of the class we have per class. And also, you can see that if we have a few amount of steps, so on the right, accuracies, so this is the average incremental accuracy of every model is very high. And they seem to all converge around the value between 60 and 64. So here, all models are quite similar, and the gain between model is very low. But as we go in a harder setting, so with more tasks but less classes per task, we can see that the accuracy of every model start to drop by a large margin. For example, if we go and see UCR CNN, at first, with a 5 step, they have an accuracy of 64. But then in the other setting, they have an accuracy of 49. So they forget a lot by a large margin. And if we see our model, for example, PODNet NME, at first, on the most right side column, it has an accuracy of 64, but then it is on the other setting at only 61. It didn't forget a lot. And maybe a table can show how much the improvement is, but a figure is better. So on the right column, on the right table, right figure, excuse me, it's kind of easy setting where all models have a similar accuracy. And on the left figure, so the figure A, this is the hard setting with a lot of tasks and a few class per task. You can see here that our model suffers from a forgetting because yes, our model is not perfect and it has some kind of gradual forgetting. So it starts from a very high accuracy and then decrease, which is also kind of normal because we're adding more classes, so the accuracy should decrease a bit. But if we saw the other state of the art, so ICARL, BIC, a CVPR from last year, and UCR, we can all see that they all suffer from literally a catastrophic forgetting. In the first 5 tasks, they lost as much as 40% of their performance. And then they all stay similar and suffer from only gradual forgetting once they are forgetting almost everything. So this is a strong problem, and we can see that most methods, which were very interesting and work well on a large setting, but we show that if we're using a very large amount of tasks with a small increments, this is a very different setting that a lot of algorithms were not prepared for. Once we evaluated and proved that our model was working well on CPR 100, we wanted to see if it was also working well on larger scale dataset such as ImageNet. So we evaluated on ImageNet 100 and ImageNet 1000. Here, For ImageNet 100, we did the same kind of step that we did for CFAR because we have the same amount of classes. So it's 50 classes at first. Then we had, for example, 50 steps of one classes. For ImageNet 1000, we did less experiment because it's very slow to train, especially in continual learning. We can see the same result where our model, PODNet CNN, is still better by a significant margin compared to against the state of the art. You can see that on the easiest setting of ImageNet 100, we beat the state of the art by at most 4 points, and on the hardest setting by 4 points. Also, you can see that we only evaluated our model on CNN and not NME because we found that NME was maybe good on a small scale dataset such as CFAR, but on larger scale dataset such as ImageNet, it was performing poorly, and we chose to focus only on the CNN version. So we proved that both in a small scale dataset and large scale dataset, our model is better than previous state of the art if we have in a setting with a few amount of classes and a few amount of classes per task, so a lot of tasks, and a few amount of memory. Finally, I said previously, we said that statistics, distilling on statistics is more robust than distilling on pixel-wise match. So we wanted to see if our model was also more robust with a different factor. So on the first table, table 4, we evaluated our model with different kind of memory size. So obviously, the more memory size we have, the easier setting is it. And if we are allowed to use the whole memory, but it's not really a continual learning setting, and it's simply retraining from scratch. So this is not a real interesting problem. You can see that the default setting was 20, so 20 images per class. If we have a lot of memory, so for example, 200 images per class, all models are quite similar. And actually, BIC, which is an algorithm that works very well with a large amount of data, is almost as good as ours. But once we start reducing the memory per task, per class, we can see that the performance of all models dropped significantly, and they converge around 20% accuracy. While, for example, PODNet enemy is almost at 50 points, so more than twice better on a very small setting. So when we have only 5 examples for the whole class memory, it's kind of a low shot setting where we have to rely a lot on the previous knowledge, and we hope that the previous knowledge is not lost too much. Thankfully, thanks to our distillation that is applied on intermediary outputs, we can see that it is not. On the table 5, we evaluate other settings also. So table 5A, we evaluated easier memory setting. So the memory setting described by iCarl, where the memory capacity can be used more easily. You can see that all performance of all algorithms is all better, but our model is still better. And finally, we evaluated on a different initial task size. And indeed, the larger the initial task size is, the better is our model, and the better is every model. Because the larger our initial task size is, the model, the feature, can be learned better, and then the distillation is more accurate, as there is less outliers compared to the whole model. And finally, we did some ablation in order to understand every setting. So we ablate to see the performance of the classifier classics, so the cosine classifier, and the LSC. So LSC is our model. So it was the local similarity classifier with several modalities, but we use a special loss. It was not softmax plus cost entropy, but it was a modified MTA. It's a loss designed in 2007 in innovates, which was very useful for setting with low amount of data. And we can see that this loss helped a lot, but we also evaluated LSC-CE, so it's our local similarity classifier with a cross entropy, which also give better result. On this table, we can understand that the main factor of improvement is the pod spatial loss. Pod spatial loss give better result. And we choose to keep the pod flat because it did bring a very little amount of performance for CNN, even if it degraded a bit the performance for enemy. Thank you all for attending. I think I'm being a bit fast, but what are your questions?
Thank you so much, Arthur, for your talk. I think it was great. So maybe I can start with a question. So I didn't quite get I mean, how many intermediate output do you consider in your loss? I mean, it's
Yes.
after each layer of the network, or
No.
the two of them?
If it will be after each layer, there will be too much.
Yeah, correct.
Our ConvNet is ResNet, and so ResNet made in several residual blocks, and we choose to focus only on the final embedding of each residual block. So our ConvNet, I think it has 4 blocks.
Yeah,
therefore
right.
we are focusing on 4 intermediate outputs.
Yeah, okay. Nice.
And
I
it was
think,
enough.
I mean, yeah. And did you try to like imposing this distillation loss also on even more blocks or
Yeah,
less?
we tried on more and less, and globally the performance was mostly the same if we had more distillation. If we did on less, the performance was worse. And what was very interesting is we wanted to see if the earliest block were more important or less important than the latest block. And actually, we didn't find a real significant gain between the old and the new one. And it seemed that we wanted to constrain as much the latest block and the earliest block, which was quite surprising to us.
Yeah, I mean, what one would expect that, yeah, the you know, the more in depth you go into the network, the more stable you want these features to be. So maybe,
yes,
yeah, having them more stable with this additional loss, especially for the higher layers in the network, will be better. But
we didn't find significant gain. So maybe there, if we can tweak it better, but I think the gain would be very little.
Thank you. Then just a comment. I think you may be interested in a paper we have written. I don't know if saying it recently, but we started a year ago about this, and it was about the name of the paper is Reaction-Free Continual Learning over small non-ID batches, and the idea was to train of very small batches with just one class and 300 images or so. So maybe interesting for your setting as well,
yeah.
because I mean we agree with you that it's much more difficult to learn continuously when you have a very small batch or task of data, and maybe you have just one class, or it's also very reasonable to get that if you have that unbalanced data, then you have more forgetting. So we try to do that even without an external memory, and we managed to at least grow in terms of accuracy over time. So it may be interesting. So
Okay,
thanks
I will
again.
check it out. How did you say it was called?
It's been accepted now as a workshop paper. It's the CL workshop at CVPR, and it's called Reaction-Free Continual Learning over small non-ID batches.
Okay, I will check it out. Thanks.
Any other questions?
It doesn't seem anyone has a question.
Cool. Okay. So thank you again, Arthur, and I invite you to post your slide if you can on Slack or on a topic we are going to create on our forum. And of course, I am going to upload this video on YouTube, and then I'm going to link this video as well in this, let's say, topic on Discord. So if you guys as well want to chat about this paper and about the topics we touched today, you can comment there on our forum. And thank you all for joining, and see you next Friday. We are going to have not a reading group session, but a meetup I'm going to announce later on next week, possibly. So you're all invited to join as well. Thank you for joining.
Thank you.
Bye.
Thank you. Bye.
Thank you very much.
Thank you for the nice talk.
Thank you.